Great. Are we fed? Are we satiated? Cool. Well, if we're not, then you're going to be fed with some science talks. So we have Chengxin Jiang, who'll be giving our next talk. Now, he is a member of AuScope Earth Imaging Team at the Australian National University. I'm going to hand you my mic.
Sure. Thank you.
And let's see if I can get you up. There we go. Take it away.
Sweet. Thank you. Thank you for actually sticking around for the last session. I really enjoyed it a lot. So today I actually want to share you with some kind of case studies that has been enabled actually by AuScope infrastructure, particularly the seismic part. So the real idea is to try to using sort of anthropogenic noise sources such as traffic to obtain high resolution images of the near surface. By near surface, I mean the top 1 to 2 kilometers, which is where the resources are. So why do I care? As I mentioned, this is what really the top 1 to 2 kilometers are the focus of the future exploration because of the thick sedimentary covers. The figure on the right-hand side we see a couple of times, but the point that I want to highlight here is that, of course, on one side, we have amazing amount of a variety of kind of resources across the continent. But at the same time, the shallow ones has been already found. Of course, the next future focus of the exploration will be the vast continent beneath that kind of cover. So for that, in terms of seismology, that really demands a cheap, environmental friendly, as a very effective approach. I think that's what passive seismology really comes in. And I think in the past 2 decades or so, passive seismology has really evolved from earthquake-based study. You got to wait for big earthquakes in order to get something decent, to something where you rely on like continuous noise source. That noise source is coming from ocean waves, cyclones, traffic, and etc. At the same time, there's also exciting opportunities enabled by, of course, the infrastructure. This is the relatively recent sort of investment from AuScope for the seismic nodes, as well as the district acoustic sensing. So on the left-hand side, we already see this exciting CRCP array we put together into the South Australia to imaging, exploring for the hydrogen. What you see here is that about 250 sites, putting together in an area of 20 by 20, a couple of days. And that's really remarkably able to, the image of the top 10, 15 kilometers of that kind of structures. Even though this image is about 1 kilometer, I guess we have a little bit kind of trouble to see even shallow of that. On the other side, distributed acoustic sensing is really exciting technology. And here on the right-hand side shows a kind of experiment led by Professor Megan Miller at ANU, which is basically a kind of dark fiber running through IMIT to Monash. What we have been able to do is enable them into like hundreds of thousands of sensors on the meter scale. What it gives us is actually unprecedented kind of image of this top 100 meter, we call like critical or subcritical kind of zone. I guess this is really exciting, but at the same time, we're asking, can we do even better? The reason for that is that, even though we have hundreds of thousands of sensors on meter scale, we have to actually do a lot of averaging in order to get something that is really, really stable. So traditional tomography, we can actually rely on a single station or station pair to do that kind of imaging. So the short answer is certainly yes. So that's where the first case come in, where we're imaging the Lake George fault zone. So there's a lot of details, innovations in terms of workflow, things like that. So if you're interested, we just actually published in SRL. So I'm just talking about the main idea. So for those who are not familiar with Lake George, it's quite a a big feature. So it's about 20 meters of drive to northeast of Canberra. Here shows like 2 images of the past, 60s and the current. Clearly, it saves you 2 hours drive for entertainment like sailing, right? But it seems that it's prohibited currently. And on the image on the right-hand side, you see 2 things. Magnitude M26, which is the main highway connecting Canberra and Sydney. Obviously, it's very, very busy. Right west of it, that's actually the foothills, where it's about over 200 meters of kind of uplift in the past 4 or 5 million years. That's the fault zone. Obviously, you need multi-million-dollar in order to actually do a seismic experiment in the water. But it turns out that there's a lot of times that they are being dry because of the climate. So here is actually the image shows where this is actually the first seismic nodal deployment we've done actually in Australia, in the academic sectors, which is Lake George seismic experiment. The figure on the left-hand side shows the kind of tweet images, which is actually picked by Megan, where get all of this kind of excited. Clearly, it turns out you will need probably very long, sophisticated process to get the permission in order to do the deployment. But during that time, at the end of 2020, I highlight up there, professors at ANU actually doing a drilling there to understand the sort of paleoclimate based on the sediments. So that's where it gets started. So here shows the top figure shows what the seismic array was looking like. 97 sensors, okay, in about like 5 transects perpendicular to the highway. So we particularly designed this kind of array to get something, at good signals. So the figure on the bottom shows how the energy, basically the frequency of energy we recorded through this kind of 4 weeks of time, and the vertical axis is the frequency. And you can see there's like cars, heavy traffic give you like very, very significant energy, not as good or as high as like a vibroseismic you would need in the active sets, but it's very, very good and cheap, right? So if you're just moving about like 2 kilometers, the energy is actually, most of them is gone. But instead, what you're picking up here is actually some activities coming from the windmills, okay? So there's a lot of details, but here I just want to show how stable the seismic phases are if you do, for example, we call seismic interferometry. Basically, you cross-correlate 2 stations at the bottom. You see the location perpendicular to that kind of highway. And then the figure on the right-hand side basically shows the average 4-hour cross-correlation function through that time. You can see how stable they are. To the rightmost, it is the correlation coefficient of each 4-hour window compared to the stacked average. Very quickly, about like a day, you get this kind of larger than 0.9 correlation. So it means give you like kind of temporal resolution that you can actually do this kind of monitoring through traffic. Not very surprisingly, during the Christmas Eve, New Year Eve, apparently the traffic condition changes significantly. That's where the waveform looks deviate quite a lot. So here, just like showing you, that waveform, and then also that bottom is that the frequency time analysis, basically telling what kind of phases, that kind of seismic signals. So what you see, that kind of trending thing, is actually what the surface wave, and you can actually harvest them very easily, of course, after a series of kind of investigation, and then use them to do the imaging. So saving a lot of details, but just want to highlight, this is actually one of the first few studies that have been managed to actually do proper seismic tomography with traffic noise. What we have been is, of course, the 3-dimensional. The top 2, just note, this is meter scale, 20, 60, and then 100 and 200. So what we see here is actually something that's very, very interesting, turns out. There's a low velocity zone, highlighted here by this, and then if you draw the cross-section, you see it more vividly, the weights as well as the kind of depths. So it's kind of over 30% of velocity reduction. What that really simply means is like rocks is really, really fractured. And that weight is actually, the seismic characteristics is very, very similar to some of the active branches of the San Andreas Fault in South California. Okay, but I guess the takeaway for this study is that it shows a kind of huge implications for exploration, not only just in industry, probably in city as well. So the second kind of case study moves really to a sort of energy sector, which is geothermal, Lake Taupo in New Zealand, where I think the earliest, one of the earliest power plant in New Zealand called Eakin. So different from the traffic noise, you can see now we have a lot of like city noise as well as like pipelines, machinery kind of things. So it becomes much complicated. But here's just illustrating the WETA array, what it's looking like. So by the way, this is actually probably the first international efforts using our AuScope kind of infrastructure for seismic component. So the figure on the left-hand side shows the 2 phases of the seismic array we have been deployed. The color just indicating 2 different kind of seismic sensors. This kind of area is showing the Lake Taupo, and then you can see there are some kind of white kind of contours illustrating the very conductive kind of probably related to the geothermal reservoir at depths of about 1 kilometer. So we are still trying to figure out understanding the noise source of particularly the traffic ones in order to do this kind of three-dimensional tomography. But what I'm going to show you, I was so excited about, is actually showing some preliminary results coming from the horizontal to vertical ratio, where Graeme actually touched on this morning. So what they really represent is the single station-based approach using the passive seismic recordings, okay? And the HVSR curve is simply, the sort of shapes, wiggles in the frequency domain. The horizontal is frequency, vertical give you the kind of amplitude. So you can see there's different colors. What that color is really reflecting is through kind of if you eject some certain waves, how it travels. And then this is when you adjusting, for example, the top 20, 30 meters kind of structure from just increasing that kind of depth, but keeping the velocity. And then this is how the responded HVSR curve looks like. So apparently it gives you a very, very exciting opportunity to characterize the first top 1 kilometer structures also. So if you just flip that kind of HVSR curve into vertical dimension, the top shows, you can regard it as like shallow structure, bottom one shows like deeper one, and then you can clearly, here just like showing a cross-section, a cross-section in the northernmost of this kind of squares, where most of the stations are, and then you can clearly see a big bump, at the very relatively low frequency, or like a high frequency, or the very shallow depths, that it seems to be dipping, okay? And then below that, there's a couple of other phases, just a little bit kind of smaller, but still there. If I just zoom in into one of them and then show you how do we get the velocity structures under that. So on the left-hand side, this is a prior we used. It's very broad, but it surprisingly, it converges really, really well. So the figure on the bottom right, you see, I think the red curve are the observed HVSR, the black curves are the fitting, and then adjacent to the left, it shows a kind of velocity structure. So clearly, we get this kind of layered model, converges very fast, and then it shows like 3 or 4 kind of major kind of boundaries. And the first one is surprisingly converged very, very well to about like 10 to 20 meters, which I interpret as a kind of probably soil layer. And then the second one, beneath that, this kind of seems to be a velocity reduction, compared to the basement rock, it has a velocity reduction, give you the shear wave velocity about like 1,500 meters per second, and I suspect this is probably related to the fracture zone where actually the hydrothermal energy are located. By the way, I just got this image about like 2 days ago, but I'm just so excited to share with you about that. So I'm actually traveling to New Zealand to talk to a lot of geological friends, so stay tuned. What's next? So what I have shared with you so far is really actually academic-enabled kind of seismic deployments. We deploy on the order of hundreds. But here is actually show you some kind of experiment. It's really enabled, or like in the data collected in the production phase for the energy exploration in the industry. This is experiment done in the Cannon Basin. There's 2 seismic arrays. I'm just highlighting the Raffle 2D array. You can see in the very similar kind of dimension where we do the South Australia array for hydrogen exploration, we have more than 22,000 channels, okay, in this kind of area. So you can imagine that's just tremendous amount of, 2 orders magnitude more kind of data. And I think we were going to transfer what we have learned in the experiment we've done, and then really to see how the passive seismology can actually help in terms of the exploration. So just to conclude, I hope I convince you that traffic noise is really a very good seismic source for us to enable the high-resolution seismic tomography in the top 1 to 2 kilometer scales, and that opens a lot of possibility for urban subsurface, real exploration industry, as well as seismic hazard mitigation. And I also show you modeling the HVSR full spectra can really help you to constrain the top 1 kilometer structures, in this case for geothermal setting. And I think this is really paving the way for future mining clean energy exploration with passive seismology in Australia. With that, I think we just thank you. Waiting for the question.
Great. We've got time for one question. Do we have a question? Anywhere? I saw a hand go up, but it was scratching her head.
Fantastic talk, thank you. It's really cool, this stuff. Do you know of any examples of where people are using active source stuff in the sorts of examples that you're talking about here, like that we could point to if we're trying to promote it as an opportunity for Australia?
You mean this one or the
Well,
last?
I
Not,
mean,
not this one.
The examples that you give at the end, you know, for like clean mining and, you know, ways that we could actually deploy these within urban environments or within industrial environments. Are there some examples from around the world where it's currently being used that we could point to?
Yeah, I think that's a good question. And I think I'll probably have to get back to you, yeah, after some digging. Yeah, thank you.
Any other questions? At the back. We have a mic runner close to you.
So the Wairaki situation looks really interesting, and how much would it cost to do that? I mean,
Right.
what are we talking about cost advantages of these sort of projects?
Right. Yeah, sorry, because of the time, I didn't put them into the context. So for the deployment itself, it's relatively cheap. Because, say, the seismic nodes is all in one passive, you know, the sensors, GPS, battery, all in one, and then you can carry probably like 6 or 7 of them just in one go. And then for the Lake George array, basically it takes about 6 folks just a day to deploy that 100 sensors. Here is slightly bigger because you have to drive around, but I think we complete, say, the first phase in about like 4 days. Yeah. But that, at the same time, because of the international kind of project, you have to dealing with like, you know, the import, yeah, things like that. That might cost a bit more, yeah.
Great. Well, thank you so much.
Thank you.
So we have, coming up, we've got Caroline Eakin, who's the Senior Lecturer in Observational Seismology and Geodynamics at the Australian National University. And I'll get your slides up.
Hello, everyone. So I'm going to be talking a bit about some AuScope-enabled research in seismology. So Chengxin has set things up very nicely for us. So we've been talking quite a bit this conference already, particularly yesterday, about how critical minerals, metals, minerals we're interested in. A lot of the particularly giant deposits are associated with regions of cratonic crust and lithosphere, and in particular the margins of those regions. This is a map globally, the pink regions being the cratons, the symbols being some of those different deposits. If we look in this example now for Australia, some key work by one of my colleagues, Mark Hoggard at ANU, published in Nature in 2020, showed that 85% of sediment-hosted base metals, things like copper, lead, zinc, in particular, again, the giant deposits, are found to lie within 200 kilometers of the edge of the thick lithosphere. So in this map behind me here, that thick lithosphere would be the blue region and the boundary between the blue and the red. And we see for Australia, does my mouse? Yeah, Australia, that blue thick lithosphere overlies the regions of the oldest cratonic Australia. So the idea here is if we can image and resolve Australia's lithosphere, in particular the boundaries within the lithosphere, then we may be able to better predict where we might find more of these giant deposits, particularly in regions under cover, as Chengxin mentioned in his introduction. So I'm going to be focusing more on the Gawler Craton and South Australia, where I've been doing work in recent years. And we see what I've always found interesting about the Gawler Craton is if you put up a map on the right, looking at metals, in this case copper, all the green symbols, regions of copper occurrences and resources. You see a lot of copper on the eastern Gawler margin. And on the left is a map of seismicity or earthquakes. So the different symbols and colors represent different magnitude earthquakes from a magnitude 4 and up. And this is from the national catalogue curated by Geoscience Australia. And you see again that the eastern margin of the Gawler Craton is associated with elevated seismicity. FR here is the Flinders Ranges, one of the most seismically active regions in Australia. On average, every 1 to 2 years, you get a magnitude 4 or above earthquake. So likely both these things, the seismicity and the copper, relate back to the crustal, the structure of the continent, where there's major faults and where we have fluids. Copper is going to be occurring along those same pathways for fluids back in the past, and today the earthquakes also relate to structures and faults and fluids, but most likely being fluid assisted today in the present. Okay. So starting in 2017, there's been a big expansion, mostly enabled by AuScope, of seismic arrays in South Australia. Back in 2017, South Australia was probably one of the most poorly seismically instrumented in terms of arrays. And on this map, we have symbols for all the different deployments. And in the bottom, the different colors, the legend in bold, I've highlighted those networks since 2017, which have been primarily AuScope supported. But the ones in white were also a deployment by the Geological Survey happening at the same time. So we were able to leverage all these data sets, increase number in particular of broadband instruments, which are really useful for imaging deeper into the lithosphere. So we've now got good coverage of this eastern Gawler margin. So I'm going to be talking about the current deployment, currently ongoing, called SNAKEY, keeping on the animal theme for many of our deployments. And this stands for Seismic Network around Kangaroo, Ayr, and York. I've got a picture here of Robert installing one of our sites in the York Peninsula. And this is a deployment of 20 broadband instruments. It's located sites along the eastern Ayr Peninsula, York Peninsula, Kangaroo Island, and sort of passing through Adelaide. So it improves our coverage in this region where often we hadn't gone onto the islands or the peninsulas and installed instruments, and this southeastern margin of the Gawler Craton. The aims here broadly are to better characterize the local seismicity and improve imaging of the crust and upper mantle structure beneath this region. So I'm going to talk through a few different sort of taster of some of the research that myself and collaborators have been doing, starting with the seismicity and the earthquakes. So this is a machine learning-based earthquake catalog that Robert Pickle has been working on. Robert's in the audience over here. And we see on this map, so now this is using all data that's available on AusPass from the year 2000 onwards. So utilizing all these temporary arrays and deployments that AuScope has supported. And again, we see all this seismicity, very active seismicity in the Flinders Ranges. It's also not just picking up earthquakes, it's picking up mining blasts. So I've highlighted some of where the major mines are in South Australia. But some of the interesting things that come out of this. Firstly, when you're using all the temporary arrays, you pick up 3 times more events compared to the national catalogue, which is only using the permanent backbone of stations, but also seismometers in schools, I should mention. When you do this, the medium depth comes out just around 3 kilometers. So we know that seismicity in Australia is pretty shallow, and the average magnitude is only 1.5. So we're picking up this very small magnitude earthquakes. Got that seismicity in the Flinders. We also, I think, interesting around Adelaide. There's quite a bit of seismicity recorded in the Adelaide basin, relative on this map. And as I'll pick up again here, and Graeme has already mentioned a little bit this morning as well, on the eastern Ayr Peninsula, we now get a more defined band of seismicity along this eastern Ayr Peninsula that seems to sort of fall in between the Kalanjala Shear Zone and the Shoal Point Fault. So that's telling us about the fault structure in this region. Another thing going deeper now is one of collaborators, JP O'Donnell, formerly of the Geological Survey of South Australia, has been imaging the lithosphere, creating new, more high-resolution models of the lithosphere in this region using all these new data sets. And this is using Rayleigh wave, type of surface wave tomography. And on the images here, we're looking at 70 kilometers depth slice and 100 kilometers depth slice. The blue colors represent fast seismic velocity, so we're looking at where we have the cratonic lithosphere, and the red colors represent where seismic waves travel more slowly. So we're less cold, we're less lithospheric. And the different colors here represent different IOCG and gold deposits. The white bars correspond to shear wave splitting. I'll talk more about that next. Ignore that for now. But what we see here is the core of the cratonic lithosphere in South Australia is sort of centered over this eastern Gawler beneath the Curnamona province and down York Peninsula. But interesting, and this has kind of been hinted at before, but really confirmed now, there's a missing piece of lithosphere beneath the southern part of the Eyre Peninsula, potentially related to that breakup and separation of Australia and Antarctica. But that's somewhat speculative. And if we take a cross-section through this model, then the triangles here represent some data from petrology, looking at xenoliths in the crust, and you can get a depth of the lithosphere or asthenosphere boundary out of that, and it agrees really well with what JP was getting from the shear wave velocities. So that's really nice to see, the petrology and the geophysics both agreeing. Okay, then thirdly, we've been also recently with SNAKEY adding to the shear wave splitting in the region. This is a project that myself and was initially by Sankarshan, shown here, was a future research talent scholar. This winter at ANU, worked with myself and with Miriam, also in the picture, who's a postdoc in my group at ANU. And this method, we're looking at the polarization of shear waves, core refracted waves such as SKS and PKS. And they're sensitive to the anisotropic fabric, or the textural fabric in the upper mantle. And essentially here we've got lots of bars plotted. Those bars show the fast direction, and they relate to the direction of maximum shear or flow in the mantle. This is hard to do whilst holding the microphone. But so the orientation of the bar and the color of the bar represent this fast direction, or you can kind of think of it like the shear direction. And this is something that's thought to, the main signal of this is thought to come from the upper mantle, the main region of seismic anisotropy. And these ones from SNAKEY here, we're seeing a good agreement of sort of the general fast direction with what we previously saw in the more northern part of the Gawler Craton. So I'll just jump to this. This is now a sort of simplified geological map in the background. And now the shear wave splitting bars are in blue. And what's interesting in the thick dashed black lines are the deformation structures that go back to the Kimben orogeny, going back 1.6 billion years. And we saw that previously in the north part of the Craton, that these fast directions were similar to these deformation structures. And now we see it again in SNAKEY. But what's really interesting, I think, along the eastern Eyre Peninsula is they're very similar to the orientation of this Kalanjala shear zone. So if I go back, they're slightly orientated in blue differently, but they're parallel to this Kalanjala shear zone. And Graeme mentioned this morning, that this is thought to have been a lithospheric scale fault. And this really confirms it, that we're seeing evidence of anisotropy preserved in the lithosphere, preserving the sense of shear along this Kalanjala shear zone. So it's confirming it's a lithospheric scale structure. And it's not on this map, but there's another shear zone on Kangaroo Island, parallel with the Craton boundary. And in red here, we have some fast directions parallel to this shear zone as well. So coming back to our original question, I think looking in more detail at the anisotropy really helps us learn more about what boundaries that we see at the surface have expression in the lithosphere, and where these, and particularly characterizing where these lithospheric scale boundaries are. Okay, so this is a summary. SNAKEY is currently filling a gap in the seismic coverage of the Gawler Craton. Work is ongoing to study the crust and the lithospheric architecture beneath this seismically active region and also mineral-rich region. Preliminary results showing that we've got, as we know, we're getting frequent seismicity in this region, and I think interestingly, including in the Adelaide Basin. We're seeing more, compared to the national catalogue, more defined bands of seismicity that are likely occurring along these transcrustal scale faults or shear zones. We're now starting to define where those faults are. We're not seeing cratonic lithosphere beneath southern Eyre Peninsula, which is really weird because there's definitely Archean and Proterozoic crust up there. The major IOCG mineral deposits are lying above, confirming again seismically fastest lithospheric mantle. So there's definitely a relationship to that lithospheric structure and where those deposits are. And lastly, that the lithosphere is preserving something telling us about the boundaries of the lithosphere, how the lithosphere has deformed in the past, and preserving that history is stored in that anisotropy. Okay, thank you.
We have time for just one question. Do we have a question? We've got a couple down here. Whoever gets it first, there we go. What's your question?
Hi, thank you. That's very interesting. And especially saying the IOCG deposit along the boundaries where you show on the map. Just wondering, do you have plan to do such study other regions such as Mount Isa? Because it'll be interesting because Ernest Henry was the second largest IOCG deposit. Would that confer your study in the sense that we do have IOCG deposits like in the area?
Yeah, so definitely where there's been these temporary arrays of broadband seismometers, that's one of the goals, to look at the more detailed the lithospheric structure. And Mount Isa is where there's been the Oz array in past 5 years, right? Mount Isa, yep. So that's definitely one of the goals at Geoscience Australia there, similar ideas about trying to better image and characterize the lithospheric boundaries there, yeah.
Well, thank you so much. We have our very last presentation of this type for this conference. And we do have Graeme Beardsmore coming up, who is the Project Director of Heat Flow Data at the University of Melbourne.
I would like to use this one. Thank you. Thank you. Hello, welcome. Thank you for staying. If I can paraphrase Arnold Rimmer from the classic British science communication program Red Dwarf from last century, I'm going to be talking about heat flow at critical zone observatories. So we need to define several words in that title. What is heat flow? What are critical zones? Why do people observe them? And why are they so frequently linked with heat flow? So before I launch into that though, I don't operate in a vacuum. In fact, I rarely operate a vacuum. This is a collaboration. It's a high-level AuScope turn collaboration, which came about through discussion between Tim and who I call the Turn Tim, whose name is Beryl at Turn, who saw opportunities to deploy AuScope equipment to investigate critical zones. Again, bit of a sidestep. I consider myself a tradesman. My trade is measuring temperatures and measuring thermal properties of Earth materials, so rocks and dirt and things. So I find myself called into projects to work on research questions that I know very little about, and critical zones was one of them. I'm rapidly coming up to speed with what critical zones are and why they are important. I'm also coming up to speed with yogurt factories, fertilizer plants, and in the past I learned a lot about barramundi, the things I could tell you about barramundi. Anyway, I stray. This is primarily a collaboration between the AuScope subsurface observatory, where I sort of operate in orbit, around that subsurface observatory, and the Critical Zone Observatory group, which operates within TURN, who's primarily David Chittlebrah and Wayne Meyer at the University of Adelaide, Sally Thompson at the University of West Australia, Martin Anderson at University of New South Wales. But also none of this work could happen without Graeme Heinsohn and his on-ground support, primarily through his PhD student David Baker, but also other just logistical support. Thank you, Graeme. Would never happen without you. And shout out to Uri Farkas, also from University of Adelaide. Edena Kamami, who works with me at Melbourne Uni, and Anu, who has been assisting at CSIRO in data management. I heard she's recently changed jobs and somebody else is stepping into that role. And there's been numerous other sort of students and other fellows who have helped out along the way. So, what is a critical zone? What are critical zones? A critical zone, I learned, is really that zone of the regolith, the shallow 10 to 20 meters where water, atmosphere, ecosystems, soil, and rock all interact. So where all life pretty much is supported through the critical zone. And we actually, we being the scientific community, have a lot of knowledge gaps in how all those mass and energy flows operate through that critical zone that supports all life as we know it, on land at least. So there's a global network of these critical zone observatories, 5 of which are operating or under development in Australia, and one of which is the focus of this talk at Kelpiram Station in South Australia. And they're really multi-sensored super sites measuring everything that's possible to be measured in terms of mass and energy transfer through the critical zone. So the focus of this work is at Kelpiram Station in the Riverland area near the Victoria-New South Wales South Australia border, about 3.5 hours drive northeast of Adelaide. And this site was chosen because it's typical of mallee scrub ecosystems. So the super site, it has lots of sensors pointing upwards for radiation, pointing downwards for radiation, weather sensors, soil sensors for soil moisture, and one of the critical elements that CZOs aim to measure is heat flux, conductive heat flux in and out of the shallow regolith. So heat conducting in, primarily during summer when it's hot at the surface, and then heat conducting back out again in winter when it's cold at the surface, but also at that lesser scale on a day-to-day basis as the sun goes overhead. So the CZO team, they tried using these sort of flux plates. So about 10 centimeters, well, this is a typical flux plate, about 10 centimeters by 10 centimeters, so buried in the shallow part of the soil with a goal of measuring conductive heat flow going in and out of the soil. But Heisenberg pointed out, though, when you try to measure something, you actually affect what it is that you're trying to measure. And there's no difference with heat flow. If you put a shallow flat pad like that and you have heat flow coming up from below, that pad actually influences the heat flow, and the heat sort of refracts and reflects through that thing, and you end up getting measurements which don't necessarily reflect the actual heat flow in the natural state. So, and not only that, but if you have something flat and solid, and you're trying to measure infiltration of water and transpiration of water back out of the soil again, those flat plates also affect that parameter you're trying to measure. So Tim was aware of these instruments, which are available to AuScope, shall we put it, called heat needles, which aim to measure the same parameter, conductive heat flow, but with much smaller footprint and much less impact on the surrounding dirt, so that it allows the natural conductive flow of heat in and out minimizing the impact of the instrument itself on that conductive flow. So it's primarily, it's a very accurate thermometer. We're in fact 7 thermometer sensors on a 1.1 meter, or within a 1.1 meter stainless steel casing. And it's drilled into the ground. The sensors are then inserted into the casing, and the control box and memory and onboard power sits in this little shielded header, and it just passively records temperature every 15 minutes, switches on, records temperature to precision sub-millikelvin, so sub-1,000th of a degree, absolute accuracy roughly 5 millikelvin, and it'll just passively record away until somebody goes back and manually stops it and downloads the data and then sets it running again. As well as that passive temperature logging capability, we can also inject a known amount of heat into the ground, and the temperature response of the needle as that heat's injected is related to the thermal conductivity of the surrounding material. And this harks back, it's quite ironic we're in this building, because Jaeger, the famous Karlsruhe and Jaeger book, so the Jaeger room just across the hallway there, they presented the about 101 combinations of mathematics to solve the equations for the thermal conductivity of the soil, depending on the parameters and the design of the heat needle and how much heat's going into it, and those sorts of things. But long story short, we get a rough profile of the thermal conductivity during our 1 hour measurement, and then we're repeatedly going back every couple of months and doing another thermal conductivity measurement and building up a time series of how the thermal conductivity of the soil is changing through time along with the temperature of the soil. So, and you multiply basically the temperature record by the thermal conductivity record, and that gives you conductive heat flow. So it's simple in concept, a lot trickier to do in practice. But February last year, so about 18 months ago now, we installed 3 of these heat needles as a pilot study at the Kelpiram CZO site in South Australia, alongside existing soil moisture sensor holes, creatively called Site A, Site B, and Site C. So Site A is roughly out in the open, away from vegetation. Site B, only about 20 meters away, but in amongst a little clump of spinifex grass. And then Site C, completing the equilateral triangle, so about another 20 meters from each of them, under a shrubbery, a mealy bush, so under canopy. So 3 of these sensors have been running for 18 months, and periodically, primarily David Baker, Graeme's PhD student, has been driving out there every couple of months to run thermal conductivity measurements, collect the temperature data. So it's a relatively busy slide, and only recently put together, only about 2 weeks ago now. So this is basically what the raw data look like. That's the temperature record here over, well, not quite 18 months, because the last bit of data hasn't been added on yet, but a year and a quarter or so of the 7 temperature sensors for the Site A sensor. Down here are those temperatures plotted vertically on the vertical scale, so 0 to 1.1 meters depth, and horizontally is time. So we're just seeing how the temperature progresses over that 15 months in that top 1.1 meters at that site. And these green vertical lines are the thermal conductivity, the inferred thermal conductivities at 5 different depths in that top meter. So with the darker the green, the higher the thermal conductivity. So thermal conductivity is not constant through time. It varies with the soil moisture, which also varies through time. But recording or multiplying the conductivity with the temperatures gives us conductive heat flow. So these are just very broad approximations. So when we first put them in, conductive heat flow was down, the ground was absorbing heat, and then a few months later, the ground was emitting that heat, and then seasonally absorbs heat in summer, and then emits that heat back again out of the ground in winter. So that's site A. Site B, similar story, but sort of subtle differences, only 20 meters away. And then site C, again, not precisely the same as either of them. So subtle differences just within sort of a couple of tens of meters away. So we can sort of compare, and there's the comparison at 1.1 meters depth of at the 3 different sites, and generally the site B in amongst the spinifex is about 1 degree warmer all throughout the year compared to the sensor under the bush. That's just a very sort of high level comparison. There's lots more could be done with the data. There's the thermal conductivity records at the 3 sites through time. So the different colored lines are the different depths. So we have sort of 6 subsurface sensors. So there's 6 colored lines there, just showing the variation in thermal conductivity with each measurement. Was that it? Big spike here in early December last year. That was 1 week after a really heavy drenching rain. So we clearly saw the impact in the thermal properties, the thermal conductivity of the ground. The waterlogged ground was considerably higher than the dry ground. But other than that, thermal conductivity is relatively constant through time. So that's just the same information plotted on a vertical axis rather than a time axis. And again, with just that blue line from the 3rd December just stands out as significantly different to all the rest. So all these data, they are available publicly on the AuScope data repository, but that in itself, these are bespoke, unique instruments. They're not available on eBay. These were lovingly handmade by myself about 15 years ago. So we had to create our own metadata schema for how to store the data. So Adena largely worked with Anu at CSIRO to develop a robust and fair metadata schema for recording these data and making them available, but they all are available on the AuScope data repository. And where to from here? So at the moment, all the focus has been on just collecting the data. There's been very little analysis of the data yet, so it's a bit of a story of my life. I spend my time just sort of developing solutions and putting the sensors in place, and then have to move on before I can actually do the interesting science on what those sensors are doing. But lots and lots of interesting information can be teased out of these data by a talented PhD student or several. And that's just sort of one pathway of the heat flow work that we're doing with AuScope. This is just a snapshot of some of the other things the team's working on. So there's Antarctic heat flow, working with University of Tasmania, Anya, if you're in the room still, and Tobias, and Joe Whittaker, also from UTAS. So we've sent some instruments down on a cruise off the coast of the Denman Glacier, working with Tobias at the moment to install temperature sensors into ice boreholes, not this coming summer, but next summer. Working with the Victorian Department of VECA, they keep changing names, Regional Development Victoria and CSIRO, to put fibre optic temperature sensors into groundwater boreholes in the Gippsland Basin to get baseline measurements before we start producing geothermal energy from that basin. And working on global data standards with GFZ Potsdam and the International Heat Flow Commission. And I'm off to Beijing on Monday to take a seat in the new International Geothermal Standards Commission to try and standardize how geothermal energy globally is reported and measured. So I'll finish on this slide because it's at the downward-looking telescope. If you look deep enough, as deep as you can, into the Earth, you see a star. You may as well be a star in the center of the Earth because little fun fact, the center of the Earth's about the same temperature as the surface of the sun. So this little image was made by the International Heat Flow Commission, sort of visualizing that there may as well be a little sun or a little star at the center of the Earth. So that's ultimately what our downward-looking telescope is seeing from my perspective, is that little star in the center of the Earth. Thank you.